Discovery of neutrons. James Chadwick discovered neutrons in 1932. For this important discovery, he was awarded the Nobel Prize for Physics in 1935. Chadwick experiment and the discovery of neutrons. In this experiment, alpha particles are projected towards the beryllium target. Beryllium in turn released another particles. These are neutral in nature. When these particles pass through paraffin wax, atoms gets charged and energized and release protons. When these protons made to enter into a gas-filled chamber, these charged protons ionized the gas. In this chamber, he placed a detector for protons. As a result of the incidence of alpha particles on beryllium, uncharged particles with same mass as protons are released. He called them neutrons.
This is our depiction of a neutron. It is composed of two down quarks and one up quark, as you can see from the tiny rings of color near the center of the quark. The overall charge of a neutron is neutral, so we have given it a silver shell. Note that we can simply add the charges of the individual quarks to give the charge of the neutron. The red, green, and blue colors of the quarks represent the color charge which generates the strong nuclear force that holds them together. It comes in three different charges, represented here by three colors, and for different colors, the force is attractive. The mediator of the strong force, the particle that is exchanged in an interaction, is a gluon. We represent gluon exchange as the occasional wispy string between the quarks. As you can see, the gluons have color themselves, and each gluon exchange causes the quark involved to swap color. Although we show quark motion inside of the neutron as leisurely, they are actually traveling close to the speed of light.
So now let us look at what happens when nuclear fission takes place. Here, the atomic nucleus is hit by a single neutron that is flying around. The impact causes the atomic nucleus to split into two new nuclei. Each of them takes part of the electrons with it, so that two new atoms are formed. In the case of some very large atoms, a few neutrons are additionally released. When uranium atoms are split in a nuclear power plant, this usually involves the release of 3 neutrons. These can then affect the next fission processes in a chain reaction. And finally, energy is released. Nuclear fusion presents a similar picture, or rather, a mirror image. It only works with small atoms, like hydrogen, for example. The atomic nucleus of the latter consists of only one proton. If one now tries to force 2 of these protons together, these 2 would have to repel each other due to their equal charge, as in the case of magnets. When talking about atomic nuclei, this is referred to as the so-called Coulomb force. This force acts as if each of our protons had a fence around it, trying to keep off other protons. Like fission needing a force that overcomes the rubber band of strong interaction, fusion also needs one that forces the protons so closely together that the fences are pulled down. And once this happens, and the protons come too closely together, strong interaction comes into play again, and makes sure that the 2 amalgamate into a new atomic nucleus. As in the case of the nuclear fusion on the Sun, It is in fact 4 hydrogen atoms, that means 4 protons, that amalgamate to form a helium atom. But as the latter only has room for 2 protons in its nucleus, the other 2 are released, similar to the excess neutrons upon the fission of uranium. And of course, this also involves the release of a lot of energy, even more than upon nuclear fission. It would only need 1 single gram of fuel, or the hydrogen isotopes deuterium and tritium, to gain as much energy as from 12,000 kilos of hard coal. This is why scientists try to develop power plants in which energy is won from nuclear fission. But how is the Coulomb force, meaning the fences around the protons, overcome? This happens by speeding up the atomic nuclei, and that happens when they are subjected to great heat or pressure. The more pressure is available, the less heat is needed. Sooner or later, 2 atomic nuclei will hit each other at such great speed that the force of the impact will overcome the Coulomb force and the protons will no longer repel each other. This is also what happens in the Sun, where 15 million degrees and a pressure of 200 million bar are necessary to amalgamate the hydrogen atoms. In a fusion power plant on Earth, we would even need 150 million degrees, as we have a lower pressure than inside the Sun. However, to this day, we have not been able to generate such high pressure in a fusion power plant.
The accelerator starts with the ISIS ion source, which creates negatively charged hydrogen ions made up of 2 electrons and 1 proton. These are then fed into the first of 3 accelerators. This accelerates the ions and focuses them, like an optical lens, for entry into the second accelerator, a LINAC. The LINAC accelerates the ions up to 35% of the speed of light. The ions are then transported to the third and final accelerator, a circular synchrotron. As they enter, the ions are stripped of their electrons by a thin foil, leaving the bare protons. The synchrotron is made up of 10 sections, each consisting of a bending magnet to keep the protons on their circular path and 5 focusing magnets. The total distance around the synchrotron is 163 meters. Electric fields provide the accelerating forces in ISIS. They also separate the protons into 2 bunches. As the proton beam is accelerated by the electric fields, the bending magnets need to become stronger and stronger to keep the beam on a circular orbit. The magnetic fields are over 10,000 times more powerful than the magnetic field on the surface of the Earth. After 12,000 revolutions of the synchrotron, the protons are now travelling at 84% of the speed of light. At this speed, they could travel 6 times around the Earth in just 1 second. The proton beam passes through a thin carbon target, producing muons for experiments before hitting the primary target to produce neutrons.
Suppose we want to produce neutrons. One way to accomplish this is with a small linear particle accelerator. We start out with 2 types of atoms. One type of atom contains a nucleus consisting of 1 proton and 1 neutron. We call this type of atom deuterium. The other type of atom contains a nucleus consisting of 1 proton and 2 neutrons. We call this type of atom tritium. Suppose we accelerate the deuterium towards the tritium. This can result in a collision which produces a helium nucleus and a neutron. The deuterium is stored in a material which we will call the filament. If current passes through the filament will heat up, causing deuterium atoms to exit. We have another material, which we will call the cathode. If current passes through the cathode will heat up, causing electrons to exit the cathode. If we then apply an electric field to these electrons, they will collide with the deuterium atoms, knocking the deuterium atoms' electrons out of their orbits. If we then apply another much stronger electric field, the positively charged deuterium atoms will accelerate towards the target, which contains lots of tritium atoms. This will create neutrons traveling away from the target in all directions at extremely high speeds. If we leave this device on, it will produce a continuous supply of neutrons.
Assalamualaikum and hello guys, we want to explain about the neutron interaction. This is neutron interaction. Hope you enjoy it. Due to the fact that neutrons are uncharged particles and do not interact via the Coulomb force, they can travel through several centimeters of material without interacting with other particles. It also can remain undetected during this process as no charge reaches the detector. Neutron nucleus reaction consists of scattering and absorption. For scattering reaction, it can be divided into two, which are inelastic scattering and elastic scattering. However, absorption reaction can be divided into two, which are capture and fission. For elastic scattering, the neutron and nuclide collide and share their kinetic energy. Total kinetic energy before and after collision are same. They rebound with different speed compared to their original speed. Residual nucleus not in excited state, whereas it remains in ground state. For inelastic scattering, the neutron and nuclide collide and rebound with different speed compared to their original speed. The residual nucleus is in an excited state. Total kinetic energy after collision is less than before collision. For capture reaction, the neutron absorbed by target nucleus to form higher isotope in excited state. The excitation of isotope emits gamma ray.
Hello and welcome to the series of instructional videos for the third year Analytical Chem Labs. I'm Dr. Robin Studley, and this video will be about the instrumental setup for neutron activation analysis. Two different instruments are used in sequence for neutron activation analysis. The two instruments are the americium beryllium neutron source and the Perkin-Elmer tricarb 2910 scintillation counter. We'll first look at the neutron source. The americium-beryllium neutron source is an alpha neutron source. In its radioactive decay, americium emits alpha particles, and the beryllium captures them and then emits neutrons. Powdered americium and beryllium are compressed together into a homogeneous pellet, forming the source. The source has an activity of 1 Curie. Neutron activation analysis begins with the sample being bombarded with neutrons. This process takes place in the activation well. Due to the fact that the neutron source is radioactive, it's not possible for us to show you the inside. However, the cross-sectional diagram shown gives you an idea of the setup. The inside of the drum is completely filled with paraffin wax, since it's a good neutron absorber, thus shielding the lab from radiation. The activation wells are holes drilled down vertically into the wax. The vials sit about halfway down the drum and are placed approximately 7 centimeters radially from the neutron source. The vials are held in fixed positions around the source. Since the wells are not identically positioned, some vials may receive more activation than others. Hence, a mathematical correction for this disparity must be done.
So in this therapy, a chemical containing the isotope of boron, boron 10, is selectively attracted to cancer cells. Now this chemical with the boron 10 is non-toxic. Your head is then beamed with neutrons, and neutrons by themselves are also non-toxic. A neutron beam isn't really going to be very dangerous at all. But where they meet, the boron 10 turns into boron 11, and that's another beast. Let's look at the nuclear equation. So boron 10 and a neutron goes to boron 11. The 10 is safe, but the 11 is very dangerous. It actually will break apart into 3 things: a gamma ray, a lithium ion actually, and an alpha particle. And this alpha particle will destroy the cancer cell.
Nuclear power's finest hour finally came in the early 1970s when war in the Middle East caused oil prices to skyrocket worldwide. Now, commercial interest and investment picked up at a dazzling pace. More than half of all the nuclear reactors in the world were built between 1970 and 1985. But which type of reactor to build, given how many different types there were to choose from? A surprising underdog candidate won the day: the light water reactor. It wasn't very innovative, and it wasn't too popular with scientists, but it had some decisive advantages. It was there, it worked, and it wasn't terribly expensive. So, what does a light water reactor do? Well, the basic principle is shockingly simple. It heats up water using an artificial chain reaction. Nuclear fission releases several million times more energy than any chemical reaction could. Really heavy elements on the brink of stability, like uranium-235, get bombarded with neutrons. The neutron is absorbed, but the result is unstable. Most of the time, it immediately splits into fast-moving lighter elements, some additional free neutrons, and energy in the form of radiation. The radiation heats the surrounding water, while the neutrons repeat the process with other atoms, releasing more neutrons and radiation in a closely controlled chain reaction. Very different from the fast, destructive runaway reaction in an atomic bomb. In our light water reactor, a moderator is needed to control the neutron's energy. Simple, ordinary water does the job, which is very practical since water's used to drive the turbines anyway. The light